Hello, hi, namaste my dear children. Welcome back to the lecture series of alcohol, phenols and ethers of Maharashtra Board Grade 12 Chemistry. This is part 5 of the same topic where we are going to discuss about the chemical properties of phenols, that is the reactions of phenols. My name is 𝐒𝐿𝐵𝗲𝐵 and you are watching 𝐿𝐵𝗲 classes. Let's get started. So when we talk about the reactions of phenols, the phenols can show these 8 types of reactions. The first is halogenation of phenols, second is nitration of phenols, and third is sulfonation of phenols. These 3 reactions all together, they are known as electrophilic substitution reaction. Electrophilic substitution reaction, where you know the substitution will take place with the help of an electrophile. What is an electrophile? That also you have seen in class 11th. Okay, so these 3 reactions are electrophilic substitution reaction. The 4th reaction is a name reaction, Rimmer-Tiemann reaction. 5th one is also a name reaction, Kolbe reaction. Then oxidation of phenols, catalytic hydrogenation of phenols, and finally we have reduction of phenols. So these are the 8 reactions where we have to study today. Okay, so let's start with the first reaction, that is electrophilic, your halogenation of phenols. Okay, now phenol undergoes electrophilic substitution reaction more easily as compared to benzene because of the OH group. Because this OH group for phenol, it is a ring activating group and it is an ortho-para directing group. Now how that is happening? Just let me show you one thing over here. So this is my phenol, and where OH is attached to the benzene ring, and you know that there are electrons in the oxygen has electrons, lone pair of electrons, and these electrons are pushed inside the rings. So we have resonating structure over here. You get oxygen as positive, and this bond, pi bond, is broken over here. So you get a negative charge over here. This bond is intact. Now this negative charge will come here as a double bond, and this bond will be broken, the pi bond. Okay, so the next resonating structures will be OH plus here. This is double bond, and this is the negative charge here now. This will form a bond, double bond here, and then this pi bond will be broken. So the next resonating structure is OH plus double bond. Sorry. This here there is a double bond. This is forming a double bond. So here there is a double bond, and this is the negative charge. Okay, now this will fall here, and this bond will be again broken. So the last resonating structures will get is this one. Oxygen will get back its lone pair, and this is the final structure. So we are saying that there are 1, 2, 3, 4, 5 resonating structures possible. Since the electrons are pushed inside the benzene ring, the ring gets more electron, that means the electron density increases inside the benzene ring, and because of that the ring gets activated. Also you can observe here the negative charge comes in the ortho position, para position, and again in the ortho position. So the attack of the electrophile will be in this position. That is why OH group is called as the ortho-para directing group. So the incoming electrophile will get attached to the ortho and para position. Okay. Now let's get back to this one. So we understood that why phenol is more prone or more susceptible towards electrophilic substitution reaction than benzene. That is because of the OH group, which activates the ring, and also the substitution takes place in the ortho and para position. So the first electrophilic substitution reaction is halogenation, halogen addition. Okay. So when phenol reacts with aqueous solution of bromine, it is aqueous solution of bromine, it gives 2,4,6-tribromophenol. Okay. So this is my phenol. You can see this is my phenol. This is treated with bromine in water. It is the aqueous solution of bromine. We get 2,4,6-tribromophenol. So the product will be, this is my phenol. The bromine will get attached to the 2 position, 2nd position, 4th position, and the 6th position. So this is called as 2,4,6 tribromo phenol. Okay, now what is happening? We need 3 bromine. So I'll be writing 3Br2 over here. 6 bromine are there. So this 3 bromine will get attached to the benzene ring, and the hydrogen which are replacing from these positions, they will be combined with another 3 bromine to give you the byproduct as 3HBr. I hope you understood. When the bromine atom gets attached over this position, the hydrogen which is already present over here, they are getting replaced, and that is why it is called as electrophilic substitution, because it is the replacement by Br+, that is the electrophile, replacement of hydrogen by Br+, which is electrophile. So that hydrogen and the another 3 bromine will be forming HBr as a byproduct. So if the same halogenation reaction is done in presence of a lower polarity solvent like chloroform, CCl4 or CS2, chloroform, carbon tetrachloride or carbon disulfide, we get a mixture of ortho and para-bromophenol. So that is how here we get a ortho-bromophenol and para-bromophenol, and para-bromophenol will be always the major product. Okay, so there are 2 types, 2 conditions for the halogenation reaction. If you are using bromine in water, that is the solvent is in higher polarity, then we are getting 2,4,6 tri-bromophenol. Chlorine will be reacting similarly. And if you are using a lower polarity solvent like a chloroform or carbon tetrachloride or carbon disulfide, we are getting a ortho-bromo and para-bromo product, para always being the major. So now we will discuss about the next electrophilic substitution reaction, which is nitration of phenol. So phenol reacts with dilute nitric acid at low temperature. Dilute nitric acid with low temperature. See the conditions over here, dilute nitric acid and low temperature. It gives a mixture of ortho and para-nitrophenol. So this is my phenol, this is phenol, and this is nitric acid. What is nitric acid? HNO3. We know that nitric acid is HNO3, so it is written as OH and NO2. NO2 is the electrophile, NO2 plus. So that is how it is written, HNO3 it is, but it is written like that. Okay, so what happens is, from here the hydrogen and this OH, this is removed as water, and NO2 gets attached to this position. So we get one product as orthonitrophenol. So this is my phenol, and in one case NO2 gets attached to the ortho position, and same thing happens from para position also. The hydrogen from the para position will get removed with OH as water. So we get para-nitrophenol also. So the byproduct here is water. So we get ortho-nitrophenol and para-nitrophenol. And as I mentioned that whenever we get ortho and para, both the products, para always will be the major product. Phenol reacts with concentrated nitric acid to form 2,4,6 tri-nitrophenol, that is picric acid. So how this reaction is, this is my phenol now, this is my phenol, and it is now reacting with concentrated nitric acid. So HNO3, and this is in concentrated form now. We get 2,4,6 tri-nitrophenol. So now the nitro group will get attached to the second position. This is my OH in the fourth position and also in the 6th position. So this is called as 2,4,6 tri-nitrophenol, which is also in common, it is called as picric acid. Okay, so we need 3 molecules of HNO3, and there will be 3 molecules of water which is coming up from here. Okay, so this in nitration also we have got 2 conditions. One is the reaction with dilute nitric acid, where we are getting ortho-nitro and para-nitrophenol, para being the major product, and one the reaction is with concentrated nitric acid, where we are getting 2,4,6 tri-nitrophenol or picric acid. This reaction is very, very, very important. All the reactions are important, but still they can ask you how to convert from phenol to picric acid. So this is the answer for that. Now we come to the last electrophilic substitution reaction, that is sulfonation. So phenol reacts with concentrated sulfuric acid at room temperature, okay, at room temperature to give ortho-phenol sulfuric acid, and at 373 Kelvin to give para-phenol sulfuric acid. Now here also we have got 2 conditions. Once the temperature is low, this is my sulfuric acid H2SO4. You can see we have just written it this way because we want to show that OH and H from here water is coming out, okay, and SO3H group will get attached. So when the temperature is low, 293 Kelvin means almost room temperature, then we get ortho-phenol sulfonic acid. So this is my phenol, and here the sulfonic acid group, that is SO3H group, gets attached to the ortho position. So this is called as orthophenol sulfonic acid, and when the temperature is little high, at elevated temperature, we get the para product. That is, this is my phenol, and the SO3H group, the sulfonic acid group is attached to the para position. So this is para phenol sulfonic acid. Okay, so here we have completed with the electrophilic substitution reaction, that is the halogenation, and then nitration, and then sulfonation. Now we will move on to the next reaction, that is Rijmer-Tiemann reaction. So the next reaction is Rijmer-Tiemann reaction, which is very important. You have to prepare it as a short note. They can ask you the question like anyway. So this is a very important topic which you need to prepare. So it is Rijmer-Tiemann reaction when phenol is treated with chloroform in aqueous sodium hydroxide. Okay, solution, aqueous sodium hydroxide solution, followed by hydrolysis with acid. That is, acidic hydrolysis is done after that. Salicylaldehyde is formed, and this reaction is known as Rijmer-Tiemann reaction. Very important. This you prepare as a short note also. So this is my phenol. Okay, and phenol is treated with chloroform, CaCl3 chloroform in presence of aqueous NaOH. Okay. So what happens here is, see this OH of NaOH and H of phenol comes out as water. Okay, so there is removal of water molecule. This O is here, Na will get attached to this, so we get sodium phenoxide. Okay, and here you get CHCl3. So one hydrogen, one chlorine. You can say this, the CaCl2 is attached. That means one chlorine from here and one hydrogen from here. They are removed as HCl. Okay, one chlorine and one hydrogen, because it is getting attached over here. So this one hydrogen from here and the chlorine will be removed as HCl. So this CHCl2 will get attached over there. This is the intermediate in this case. This is intermediate. I hope you understood. Phenol is treated with chloroform in presence of sodium hydroxide solution. Water is removed like this. So you get sodium phenoxide, Na gets attached over here, sodium phenoxide, and from here the hydrogen and one of the chlorine comes out as HCl. The remaining part, that is CaCl2, gets attached to the ortho position. Okay. Now again it is treated with NaOH. Again it is treated with NaOH. So you get sodium phenoxide and CHO group attached over there. Okay. Now how this CHO is forming? So basically this is 1 minus HCl will happen. That is, suppose this hydrogen and one chlorine is getting out from here. Another chlorine is there which will be attached as NaCl, will be coming out as NaCl. So from this two chlorine, how do I show you? From this two chlorine, one chlorine will be coming out as NaCl, one chlorine and Na will come out as NaCl, and hydrogen and another chlorine will be coming out as HCl. So what is remaining? Only OH. So that OH gets attached with the carbon. So that is CHO group. You can think like this to remember. Okay. Na and Cl is coming, H and Cl is coming. Remaining is only OH which is getting attached. So you are getting that. Okay. So now this is followed by acidic hydrolysis H3O plus, where this CONA will again come back to OH. So this is called as salicylaldehyde. Salicylaldehyde. This is salicylaldehyde. Okay, orthohydroxybenzaldehyde is also called as salicylaldehyde. Commonly it is known as salicylaldehyde. Now this particular reaction, if you use carbon tetrachloride in place of chloroform, then you are getting salicylic acid. Salicylic acid means only the CHO group will be converted into COOH. Remember, if you are using carbon tetrachloride here instead of CaCl3, that is chloroform, we will get salicylic acid. Okay. So this is your Rijmer-Tiemann reaction. So now we proceed to the next reaction, and the next reaction is again a named reaction, that is 𝐔𝐤𝐵's reaction. This is also very important reaction. Here the treatment of sodium phenoxide. We start with sodium phenoxide. We know how to prepare sodium phenoxide. Phenol is treated with NaOH because phenol is acidic in nature, NaOH is base in nature, so acid and base will combine together to give you the sodium phenoxide salt. So sodium phenoxide is treated with carbon dioxide at 398 Kelvin and under pressure of 6 atmosphere, followed by acid hydrolysis, salicylic acid is formed, and this particular reaction is known as 𝐔𝐤𝐵's reaction. So these two reactions, 𝐒𝐥𝐻 and 𝐂𝐥𝐻, both are very important. You need to prepare them as short notes. So here we start with sodium phenoxide, and that is treated with carbon dioxide at 398 Kelvin and 2 to 6 atmosphere pressure. You get OH and COO-NA gets attached over here. So you can see this COO, there is a rearrangement also, Na comes in the next position. So you get COO-NA and OH. This is a sodium salt of phenol, you can say, and then acidic hydrolysis will convert this COO-NA into COOH, which is called as salicylic acid. Okay? So these two reactions you have to prepare very well. Now come to the next reaction, that is oxidation of phenol. Phenol on oxidation with chromic anhydride, which is an oxidizing agent, or sodium dichromate in presence of H2SO4 gives para-benzoquinone. The product is para-benzoquinone. So this is phenol. Okay, I have written it this way. I just have rotated the molecule. So this is phenol. It is treated with chromic oxide or sodium dichromate in presence of H2SO4. So you get this compound as a product. This is para-benzoquinone. Double bond O. This is called as para-benzoquinone. Okay, so this is the oxidized product. Also we need to know that phenol oxidizes slowly, giving a dark colored mixture in presence of air. Okay, it gives a dark colored mixture in presence of air. The next reaction of phenol is catalytic hydrogenation of phenol. Catalytic hydrogenation means hydrogenation is hydrogen addition. Catalytic means in presence of catalyst. So it is a catalytic hydrogenation. So phenol on catalytic hydrogenation gives cyclohexanol. In this reaction, a mixture of vapors of phenol and hydrogen is passed over nickel catalyst at 433 Kelvin. Okay, so you understood the whole process. This is my phenol. It is the phenol vapors and hydrogen are passed over nickel catalyst. This is the catalyst at 433 Kelvin. So we get cyclohexanol. What is cyclohexanol? OH group attached over here. This is called as cyclohexanol. Cyclohexane, and then OH is attached to the ring. So that is cyclohexanol. Okay. The last reaction of phenol is reduction of phenol, where phenol is reduced to benzene on heating with zinc dust. Very important. Phenol is reduced to benzene on heating with zinc dust. So we are heating phenol with zinc dust. This is in the form of dust. Okay. What happens is this oxygen comes with zinc, so you get phenol. If oxygen goes with zinc, this is benzene, you get benzene, okay, plus ZnO. So basically oxygen has gone with zinc, hydrogen is here means it is nothing but benzene. Okay, so this is the reaction where you convert phenol into benzene. So with this reaction we have completed with the chemical properties of phenol. Now in the next class or next video, I will be coming up with the third compound of this chapter, that is ether. So we start with ether. If you feel these videos are beneficial to you, please subscribe the channel and press the like button. Also, if you have missed to see the previous videos of the same chapter, you can just type alcohol, phenol and ether by Arpita classes. You will get all the previous videos of the same chapter. Also, halogen derivatives are also discussed nicely. The main part of these videos are along with discussion explanation. The write-up is also nicely given, so you can also use the same write-up for your board papers. Thank you so much. Stay tuned for the next video.